The universe was born without a single living thing. Then, something changed forever. We are about to explore the greatest mystery of all, the moment non-living chemistry sparked into life. This is the profound quest of abiogenesis, the search for the universe's very first organism. You will journey through 30 of the most compelling, bizarre, and scientifically fascinating theories that attempt to solve this ultimate puzzle. We will travel from the deepest ocean vents on Earth to the hearts of distant stars, from the idea that life began in clay to the possibility it was planted here by design. By the end, you will have a complete map of humanity's boldest guesses about our own cosmic origin story. Did life simmer in a primordial soup or arrive frozen inside a comet? What does it truly mean to be alive in the first place? Which idea feels like it holds a piece of the truth to you? Our story begins with a simmering ocean under a hostile sky. This is the world of Theory 1, the primordial soup. Picture Earth over 4 billion years ago, a young planet still cooling from its violent formation. Its atmosphere was nothing like the air we breathe today. Instead of oxygen and nitrogen, it was a thick, toxic cocktail of methane, ammonia, water vapor, and hydrogen. Beneath this alien sky, vast oceans churned, warmed by a young sun and bombarded by relentless ultraviolet radiation. It was in this seemingly inhospitable place that two scientists, Alexander Oparin and J.B.S. Haldane, proposed life could have cooked itself into existence. Their idea was deceptively simple. The energy from lightning strikes volcanic heat, and that intense solar radiation could have acted like a cosmic chef, stirring the simple gases in the atmosphere and oceans. Over millions of years, these random chemical reactions would have slowly built more and more complex organic molecules, the very building blocks of life, until the oceans became a rich prebiotic broth. This was the primordial soup, a nutrient-rich medium where the first spark of life could finally ignite. The theory moved from bold speculation to startling reality in the early 1950s. A young graduate student named Stanley Miller, working with his professor Harold Urey, decided to test the idea in a laboratory. They built a remarkable glass apparatus meant to mimic the early Earth. One flask held water representing the ancient ocean. Another was filled with the proposed early atmosphere gases, methane, ammonia, and hydrogen. They then sent electrical sparks simulating ancient lightning crackling through the gaseous mixture. For just over a week, this miniature world churned and sparked. When Miller analyzed the water at the bottom of the apparatus, he found something astonishing. It had turned a murky brown and red, and within it were several of the 20 amino acids that form the proteins essential for all known life. It was a monumental result. For the first time, someone had shown that the basic ingredients of life could arise from simple, non-living chemistry under conditions that might have existed on the early Earth. The Miller-Urey experiment became an icon of science, a powerful piece of evidence that life's origins might be a natural, even inevitable, chemical process. The primordial soup hypothesis has shaped the search for life's origins for generations. It gave scientists a tangible starting point, a recipe to test and explore. Yet, like any good theory, it has faced intense scrutiny and evolved over time. One of the biggest debates centers on that very atmosphere Miller and Urey recreated. More recent geological evidence suggests Earth's early air might have been less reducing, containing more carbon dioxide and nitrogen and less methane and hydrogen. This different mix could make the formation of amino acids more difficult, though not impossible, under those classic lightning strike conditions. Another challenge is the next step. Creating amino acids in a soup is one thing, but getting them to link together into proteins and then organizing those proteins into a self-replicating system is a leap of staggering complexity that the soup model alone does not fully explain. Where did the instructions come from? How did a boundary form to separate this fledgling life from the surrounding broth? The soup provides the ingredients, but the recipe for the chef itself remains elusive. Still, its core principle endures, the idea that life emerged from a gradual chemical evolution, a slow climb from simplicity to complexity, powered by the raw energy of a young planet. It is the foundation upon which nearly all other theories are built, the first and most enduring answer to the question of where we began. But the ocean's surface was not the only kitchen available. Far below the waves, at the crushing, sunless depths of the seafloor, another candidate for life's cradle was waiting to be discovered. This is Theory 2, the world of deep-sea hydrothermal vents. Abandon the idea of a warm, sunlit soup. Instead, descend into perpetual darkness where the only light comes from the eerie glow of superheated water meeting the icy abyss. Here, along the seams of Earth's tectonic plates, the planet itself bleeds heat and chemistry. Towering mineral structures rise from the seabed like ghostly castles. The most famous are the black smokers, billowing clouds of dark, particle-rich water heated to blistering temperatures by magma below. But there is another, perhaps even more promising type, known as alkaline or white smokers. Places like the Lost City hydrothermal field, where shimmering white chimneys of calcium carbonate rise in delicate, otherworldly spires. These vents are not powered by volcanic heat alone, but by a chemical reaction between seawater and the mantle rock below. What makes these deep-sea environments so compelling as a birthplace for life? They are not just a source of heat, they are natural electrochemical power plants. The porous rock of the vent chimneys acts like a sponge, filled with a labyrinth of microscopic compartments and tunnels. These tiny pores could have served as the very first protective cells, sheltering delicate early chemistry from the vast, diluting ocean outside. More importantly, these vents generate a steady, reliable gradient. On one side, you have the hot, alkaline, hydrogen-rich fluid spewing from the Earth's interior. On the other, you have the colder, more acidic ocean water. Where these two fluids meet across the thin mineral walls of the vent, you get a natural proton gradient, a fundamental form of usable energy that all living cells still use today to power themselves. This is where the theory gets its most elegant detail. The mineral walls of these vents are rich in iron and sulfur. Scientists like Gunther Wachtershauser proposed that these metals could have acted as the earliest catalysts, jump-starting the core metabolic reactions of life right on their rocky surfaces. In this view, life did not begin as a free-floating cell in a soup, but as a chemical film clinging to the warm, mineral-rich pores of a rocky chimney. Metabolism came first, a simple cycle of energy-harvesting reactions, and genetics came later. The vents provided everything, a constant flow of energy-rich chemicals, a safe haven in microscopic compartments, and a ready-made catalytic surface to kickstart the whole process, all independent of the chaotic, ultraviolet blasted surface world above. It is a vision of our origins that is both profoundly alien and deeply connected to the planet's own fiery heart. The vents offered a perfect kitchen, but what was cooking inside it? The next theory tackles the most famous chicken and egg problem in all of biology and proposes a molecule that was both the chicken and the egg. This is Theory 3, the RNA world. For life as we know it, there is an elegant, interdependent cycle. DNA stores the genetic instructions, the master blueprint. Proteins do the work, building structures and speeding up chemical reactions as enzymes. But there is a glaring paradox in this beautiful system. DNA needs proteins to replicate and to read its own instructions. Proteins cannot make themselves without the instructions coded in DNA. So which came first? The answer might be a molecule that has been hiding in plain sight, performing critical roles in every cell on Earth, ribonucleic acid or RNA. RNA is DNA's close chemical cousin. It can store genetic information just like DNA, but in a stunning discovery in the 1980s, scientists found that RNA can also act as an enzyme. They called these catalytic RNA molecules ribozymes. Here was a single substance capable of performing both of the essential functions of life, information storage and chemical catalysis. The implications were revolutionary. It meant that a world before DNA and proteins was not only possible but plausible. In the RNA world hypothesis, the first truly living systems were not cells but self-replicating RNA molecules. Imagine a probiotic environment, perhaps within the tiny pores of a hydrothermal vent or on a sun-warmed clay bank. Through random chemistry, a strand of RNA forms that, by its very shape and structure, can act as a primitive catalyst. By chance, this catalyst helps link together chemical building blocks to form a copy of itself. It is not a perfect copy, mistakes happen. But those mistakes are variations, and some of those new variants might replicate a little faster or a little more accurately. Suddenly, you have competition, selection, and evolution, the core drivers of biology, all happening in a molecule. This RNA-based life would have been incredibly simple, a naked strand of genetic code replicating and evolving in a protective niche. Over immense stretches of time, this RNA world would have grown more sophisticated. Some RNA molecules might have begun specializing, some getting better at replication, others at catalysis. Eventually, the more stable DNA could have taken over the long-term storage of information, while the more versatile proteins took over most of the catalytic work, leading to the complex three-part system we see today. The RNA world is elegant and powerful, but it faces its own profound mystery. Where did the RNA molecules themselves come from? RNA is a complex polymer, and forming it from simple probiotic chemicals is a difficult, multi-step process that scientists are still working to recreate. It is the ultimate bootstrap problem. How do you get a molecule sophisticated enough to kickstart evolution from chemistry that has no direction at all? Yet, the discovery of ribozymes proved that RNA has the talent for the job, making it the strongest candidate we have for the original molecule of life, the pioneer that first learned to copy itself and set the whole story in motion. RNA solves a chemical puzzle, but it still places life's spark here on Earth. What if that spark came from somewhere else entirely? This is theory 4, panspermia, the idea that life's seeds are scattered everywhere in the cosmos and Earth was simply fertile ground where they took root. The basic premise is both simple and profound. Imagine microscopic life forms, hardy bacteria or their precursors, trapped deep within a chunk of rock or a ball of ice. This cosmic stowaway gets ejected from its home world by a planetary impact, and then spends millions of years drifting through the silent void. Eventually, its journey ends in the atmosphere of a young, welcoming planet like Earth, where it crashes to the surface and begins a new biological dynasty. It is the ultimate relocation story, suggesting we may all be descendants of interstellar immigrants. The idea is ancient in spirit, but found a scientific voice with the Swedish chemist Svante Arrhenius in the early 20th century. He proposed the theory of radiopanspermia, suggesting that the gentle pressure of starlight itself could propel microscopic spores from one star system to another. In the 1970s, the brilliant minds of Francis Crick and Leslie Orgel offered a more directed version called directed panspermia. They pondered with seriousness whether life could have been intentionally seeded on Earth by an advanced extraterrestrial civilization, a scientific experiment or an act of cosmic gardening. While that specific idea remains highly speculative, the broader concept of panspermia gained serious traction from discoveries right here at home. We found extremophiles, microorganisms thriving in places once thought utterly sterile, boiling acid pools, crushing ocean depths inside nuclear reactors, and frozen in Antarctic ice for millennia. If life can survive such extremes on Earth, then surviving a long, dormant journey through space, shielded inside a rock, seems less like fantasy and more like a plausible feat of biological endurance. Experiments on the International Space Station have even shown that some bacteria and lichens can survive for years in the vacuum and radiation of low Earth orbit when protected by just a few millimeters of rock. Panspermia offers an elegant solution to one problem: the apparent speed with which life emerged on our planet. Geological evidence suggests life appeared not long after Earth cooled enough to have liquid water, a relatively short window in cosmic terms. If the building blocks or even the first living cells were delivered ready-made, it helps explain that rapid start. Yet, for all its interstellar grandeur, panspermia has a critical limitation. It does not actually explain the origin of life, it simply moves the mystery to another location. If life arrived here from Mars on a meteorite, then how did life begin on Mars? If it came from another star system, the question only recedes further into the cosmos. It is a theory of distribution, not genesis, but it fundamentally reshapes the question, transforming our search from a local event on one planet to a potential galaxy-wide phenomenon. It suggests that if life can travel, then the tree of life might have roots stretching across light years, and we may be just one branch on a truly universal family tree. The idea that life was delivered here intentionally is a staggering leap in scale. Directed panspermia takes the concept of cosmic seeding and infuses it with purpose, suggesting that an advanced civilization, perhaps long since vanished, deliberately sent the spark of life to our young planet. This is not a random meteorite impact, but a targeted act of creation. The motivations we could ascribe to such beings are as fascinating as the act itself. Perhaps it was a grand scientific experiment, a way to study how life evolves under different planetary conditions, with Earth as one petri dish among many. Maybe it was an act of preservation, a way to ensure the survival of their own biological legacy after a catastrophe in their home system, scattering their genetic heritage across the stars like a farmer sowing seeds. Some have even pondered a more philosophical driver, a form of cosmic gardening or artistic expression, where the cultivation of life across the galaxy is seen as the highest purpose. The implications are profound. If true, it would mean our entire evolutionary history, from the first microbe to the human mind, was set in motion by an intelligence we cannot yet comprehend. It transforms the narrative of our origins from one of chance to one of design, raising deep questions about whether we are alone or merely the distant offspring of a forgotten parent culture. Yet, for all its dramatic appeal, directed panspermia shares the core limitation of its parent theory. It does not solve the mystery of life's ultimate beginning, it simply relocates it to another time and place. We must still ask, how did that advanced civilization originate? The question of the very first spark is merely pushed back one step into the deeper past of another world. It remains, however, a powerful thought experiment that challenges our perspective. It asks us to consider whether the universe might be filled not just with life, but with the architects of life, and whether our own existence is part of a story far larger than we have ever dared to dream. Yet for all its promise, RNA remains a delicate and complex molecule. Its very sophistication begs a deeper question. Could the first self-replicating system have been made from something far simpler, far more robust, and utterly inorganic? This is Theory 6, the clay hypothesis, a vision of life that begins not in water but in mud. Proposed by the chemist Graham Cairns Smith, this idea turns our entire organic-centric view on its head. He argued that the first life was not organic at all but mineral. Picture the silicate crystals found in common clay. As these crystals grow in a solution, they do not form perfectly. Defects occur, tiny misalignments in the atomic lattice. When a crystal breaks and new layers grow on top of these imperfections, the pattern of defects can be copied. In essence, the crystal replicates its own flawed structure. Here, Cairns Smith saw the glimmer of a primitive genetic system. information could be stored not in a complex chemical code, but in the stacking sequence of mineral layers, a geological fingerprint passed down through generations of crystal growth. This inorganic genetics would have been incredibly sturdy, able to withstand the harsh conditions of the early Earth far better than any fragile strand of early RNA. But clay is not just a passive data storage device. Its surface chemistry is powerfully catalytic. The charged, layered surfaces of clay minerals are excellent at attracting and holding simple organic molecules, bringing them close together and providing a template that encourages them to link into longer chains. Imagine amino acids or the building blocks of RNA sticking to a flat clay surface like sticky notes on a bulletin board, arranged in just the right way to react and form more complex polymers. In this scenario, clay acts as both the first replicator and the first enzyme, a mineral nursery gently shepherding organic chemistry toward complexity. Over immense spans of time, the organic molecules being fostered on these clay surfaces would have grown more sophisticated, eventually forming networks that could carry out their own reactions. At a critical point, this organic chemistry would have learned to replicate itself, independent of the clay template that gave it birth. The inorganic mineral life, having served its purpose as a scaffolding, was then usurped by its more versatile organic offspring. The clay world was relegated to the background, and the carbon-based biology we know took center stage. It is a humble, almost philosophical origin story. It suggests that the spark of life is not a property of carbon alone, but a more fundamental principle of information and replication that can manifest in the most ordinary of materials. Before there was a genetic code written in molecules, there may have been a code written in stone, a slow, silent geology that patiently built the stage for all the biology that was to follow. Cold is not the absence of life, but a different kind of crucible. Theory 7 proposes an ice world, a cradle of crystal and quiet. It challenges our deepest instinct that life requires warmth and liquid water, suggesting instead that freezing temperatures provided the perfect protective laboratory for life's first delicate steps. Picture not a steaming vent or a warm pond, but a global ocean partly frozen under a faint young sun. Within the intricate lattice of sea ice, a remarkable process unfolds. As seawater freezes, it pushes impurities, salts, and organic molecules away from the pure ice crystals, concentrating them into tiny, briny channels and pockets. These microscopic pores become hyper-concentrated chemical reactors. Molecules that would drift apart in a vast, warm ocean are forced into intimate, frequent contact, dramatically increasing the chance they will react and form more complex structures. This icy matrix also acts as a natural shield. The early Earth's surface was bombarded with ultraviolet radiation from the sun, radiation powerful enough to shatter the very organic molecules life needed to build itself. A layer of ice, even just a few inches thick, provides a perfect sunscreen, filtering out that destructive energy while still allowing chemical reactions to proceed slowly within its protected chambers. The cold itself offers another crucial advantage: stability. For fragile early molecules like the strands of RNA from our previous theory, warmth is chaos, causing them to wiggle and break apart before they can accomplish anything useful. In the cold, these structures become more rigid and stable. They can hold their shape long enough to act as a template or a catalyst, allowing for slower, more deliberate chemical reactions that would be impossible in a hot, turbulent environment. An ice world gives time, the most precious commodity of all, for complexity to emerge not in a frenzied instant, but through millennia of patient, frozen chemistry. This vision expands the search for life's origins beyond tropical Earth. It makes the icy moons of our outer solar system, like Jupiter's Europa or Saturn's Enceladus, with their global oceans locked under thick icy shells, not just potential havens for life today, but plausible models for how life could have begun anywhere. The theory elegantly solves several problems at once: concentration, protection, and stabilization, painting a picture of life as a patient sculptor, slowly carving its first forms from the stillness and the cold. Those tiny, protective pores in ice or clay offered shelter, but they were borrowed homes. What if the first living thing built its own walls from the very start? This is Theory 8, the lipid world, a perspective that flips the script entirely. It argues that the fundamental breakthrough wasn't a clever molecule that could copy itself, but the simple act of drawing a boundary. The first step to being alive might have been the decision to be separate. The key players here are lipids, fatty molecules that have a split personality. One end loves water, it is hydrophilic. The other end fears water, it is hydrophobic. When you put enough of these molecules into water, they don't just float around. They self-assemble, arranging themselves to hide their water-fearing tails and show their water-loving heads. The simplest result is a micelle, a tiny spherical droplet. But with the right conditions and slightly more complex lipids like phospholipids, they form something far more elegant, a bilayer. This is a two-layered wall, a flexible, stable membrane that creates a sealed interior space, a bubble completely separate from the outside world. These bubbles are called vesicles, and they are the candidates for our very first protocells. The magic is that this isn't a difficult, rare event. It happens spontaneously, a natural consequence of chemistry and physics. On the early Earth, in tidal pools or near hydrothermal vents, such vesicles could have formed by the trillions. Now imagine one of these tiny bubbles. It isn't empty. As it forms, it randomly traps a handful of chemicals from the surrounding soup inside its watery interior. Suddenly, you have a miniature, isolated laboratory. The membrane does more than just contain, it concentrates. Reactions that would be too diluted in the open ocean can now proceed inside this tiny compartment. And the membrane itself is dynamic. It can grow by incorporating new lipid molecules from the environment. As it gets bigger, it becomes unstable and can spontaneously divide, pinching into two daughter vesicles, each containing a sample of the original interior cocktail. Here is where selection enters the picture, even before genetics. Some vesicles, by pure chance, might trap a combination of chemicals that makes their membrane a little more stable, allowing them to last longer. Others might trap a pigment that absorbs a bit of sunlight, providing a tiny energy advantage. These lucky vesicles would grow and divide more reliably than their neighbors. They wouldn't have genes, but they would have inheritable properties, a form of prebiotic selection based on simple chemistry and survival of the most stable container. In the lipid worldview, metabolism and compartmentalization came first. The genetic code, the RNA or DNA that would eventually provide precise instructions, was a later innovation. It evolved inside these stable, self-perpetuating bubbles because it offered a better way to replicate successful chemical recipes. The vesicle was the invention that made everything else possible, a private haven where fragile chemistry could experiment in peace, away from the infinite dilution of the open sea. It suggests that the urge to be an individual, to define a self against the vast non-self of the universe, might be the most ancient biological impulse of all. Energy is the universal currency of life. Every cell in your body, from a neuron firing a thought to a muscle fiber contracting, runs on the same ancient power source, a proton gradient. This is not just a feature of life, it is its most fundamental, non-negotiable requirement. Theory 9, the proton gradient hypothesis, frames the origin of life not as a search for the first molecule, but as the solution to an energy crisis. How did inert matter first plug itself into a reliable power grid? The answer may lie in the very same alkaline hydrothermal vents we explored earlier, but with a brilliant, specific twist from biochemists like Nick Lane. He proposes that life did not invent its power system, it inherited one directly from the planet. Picture that vent chimney again, a porous, rocky interface between two worlds. On one side, surging up from below, is hot, hydrogen-rich alkaline fluid. On the other side is the cooler, more acidic ancient ocean. Where these two fluids meet through the labyrinth of microscopic pores in the rock, a profound difference exists. It is a difference in proton concentration, what chemists call a pH gradient. Protons, which are simply hydrogen ions, naturally want to flow from the acidic ocean side, where they are abundant, into the alkaline vent fluid, where they are scarce. This desire to flow, to equalize, is a form of potential energy like water held behind a dam. And crucially, the mineral walls of the vent are not perfect seals. They are leaky, allowing a slow, natural trickle of protons to seep through. This natural seepage is a geochemical current, a power stream generated entirely by planetary geology. Lane's revolutionary idea is this: the first living systems were not free-floating entities, but chemical reactions that learned to tap into this pre-existing power line. Imagine a simple organic molecule lodged in the wall of a vent pore. As protons naturally flow past it, that flow could drive a chemical reaction, perhaps forcing carbon dioxide and hydrogen to react to form a more complex organic compound, storing some of that flow's energy in a chemical bond. This is the essence of metabolism, taking energy from one source to build useful structures. In this view, the first spark of life was not a replicating molecule, but a self-sustaining chemical reaction cycle powered by the planet's own proton gradient. Genetics and replication came much later as a way to record and perpetuate the most successful of these energy-harvesting chemical recipes. The beauty of this theory is its profound continuity. It explains why every living cell, from the simplest bacterium to the largest redwood, still uses a proton gradient across a membrane as its core power source. It is a relic, a biological fossil of that first moment when chemistry plugged into a geological battery. Life did not have to invent the wheel, it simply learned to steer a cart that was already rolling downhill, driven by the relentless thermodynamics of a young, chemically active planet. The universe was not just a sterile void waiting for Earth to invent life. It was already a chemical factory on a galactic scale. This is Theory 10, the world of cosmic dust and interstellar clouds. To find it, you must look beyond our planet, beyond our solar system, into the dark, cold nurseries between the stars. Drifting through the vast expanses of our galaxy are immense, diffuse structures called molecular clouds. These are not clouds of water vapor, but colossal agglomerations of gas and, most importantly, fine, microscopic dust, primarily silicates and carbon compounds. These clouds are frigid, only a few degrees above absolute zero, and dark, shielded from starlight by their own thick veils. And within these seemingly barren, frozen depths, astronomers using radio telescopes and spectroscopy have made a stunning discovery. The space between the stars is not empty, it is rich with organic chemistry. By analyzing the specific wavelengths of light these clouds absorb or emit, scientists have identified the spectral fingerprints of over 200 different molecules. The list is astonishing. It includes simple compounds like water and ammonia, but also far more complex ones like acetic acid, the main component of vinegar, and even amino acids like glycine. Most remarkably, they have found sugars, including glycolaldehyde, a simple sugar that can react to form ribose, a key component of RNA. How is this possible in the cold vacuum of space? The secret lies on the surface of those tiny dust grains. In the near absolute zero of a molecular cloud, atoms and simple molecules that bump into a dust grain don't just bounce off. They stick, freezing to the surface in a layer of frost. Over millions of years, this icy mantle grows, and cosmic radiation zipping through the cloud provides the energy to break and remake chemical bonds on these frozen specks. The dust grain acts as a microscopic laboratory bench, holding ingredients in place and providing a surface for them to meet and react, shielded from the harsh radiation that would break them apart in open space. Slowly, molecule by molecule, complexity builds on these cosmic moats. This means the fundamental building blocks of life are not unique to Earth. They are cosmic commodities forged in the hearts of dying stars that spew carbon and oxygen into the galaxy, and then assembled on the surfaces of interstellar dust in the quiet, frozen dark. The implication for our own story is profound. When the solar system formed from the collapse of such a molecular cloud, all of these pre-built organic compounds were incorporated into the mix. They became part of the comets, asteroids, and planetesimals that eventually coalesced into planets. The late heavy bombardment, that period of intense asteroid and comet impacts on the young Earth, was not just a cataclysm. It was a delivery service. Icy comets and carbon-rich meteorites could have showered our planet with a pre-made starter kit for life, a rich supply of amino acids, sugars, and other critical organics that had been brewing in interstellar space for billions of years before Earth even existed. This theory dramatically widens the stage for life's origins. It suggests that the most difficult steps in prebiotic chemistry, the formation of those first complex organic molecules, might not have happened in Earth's oceans at all. They may have been an inevitable product of universal astrophysical processes written into the chemistry of the cosmos itself. The question then shifts: if the universe is so good at making life's ingredients, how many other worlds received a similar delivery, and what did they choose to cook? The cold chemistry of space delivered the ingredients, but Earth itself provided a kitchen with a very specific, rhythmic heat. Theory 11 takes us to the edge of a volcanic hot spring, a place where land, water, and fire meet in a dynamic dance. This is not the deep, steady pressure of a hydrothermal vent, nor the vast dilution of an open ocean. It is a shoreline environment, a shallow pool fed by mineral-rich water bubbling up from geothermal heat below, perhaps on the slopes of an ancient volcano. The magic here lies in the cycle, the constant interplay between wet and dry. Picture a small, warm pool, rich with the organic compounds delivered by comets or formed in the atmosphere. The sun beats down and slowly the water evaporates. As it does, everything dissolved within it becomes more and more concentrated. Amino acids and other building blocks, which floated harmlessly apart in the deeper water, are now pushed together on the damp surface of rocks or in the thinning film of water. They are forced into intimate contact, then the conditions change. A rain shower falls or the hot spring surges, flooding the area with fresh, mineral-rich water. The concentrated organics are submerged again, but now they are not just floating freely. They are plastered against the surfaces of clay or volcanic rock, and the new influx of water and different minerals can trigger the next critical step: polymerization. This is the process of linking small molecules into long chains. Those concentrated amino acids, when warmed and wetted again on a catalytic mineral surface, could link together to form peptides, the shorter cousins of proteins. The dry phase concentrated the ingredients, and the wet phase provided the energy and medium for them to link up. This wet-dry cycling is a relentless natural pump. Each cycle takes a random mixture of chemicals and nudges it toward greater complexity, drying them into a dense paste on a rock, then re-wetting them to react over and over again for thousands of years. The environment itself is a rich toolkit. The volcanic rocks and clays at the spring's edge are not passive bystanders. They are filled with metallic minerals like iron, zinc, and sulfur, which can act as catalysts, dramatically speeding up these linking reactions without being consumed themselves. Different minerals might favor the formation of different kinds of molecules, creating a diverse chemical playground. This theory elegantly bridges a major gap. It provides a plausible, natural mechanism to move from the simple building blocks we know can form in space or in the atmosphere to the more complex polymers that are the hallmarks of life. The hot spring edge is not just a place where chemicals exist. It is a place where they are processed, organized, and upgraded by the planet's own geothermal heartbeat. It turns a random chemical soup into a workshop where the relentless rhythm of evaporation and flow acts as a clumsy but effective assembler, slowly building the pieces of a much larger puzzle. That wet-dry cycle organized the ingredients, but where did the recipe come from? A radical answer lies not in a molecule, but in a metabolic spark, a chemical fire that burned before genetics ever existed. This is Theory 12, the iron-sulfur world, championed by the chemist Gunther Wachter. His vision turns away from the quest for the first replicator and asks a more fundamental question: what is the core purpose of a living thing? To consume energy and use it to build order from chaos. He proposed that life began as this very process, as a self-sustaining chemical cycle clinging to a rock, specifically a surface of shining metallic pyrite, often called fool's gold. Pyrite forms in hydrothermal environments, and its surface has a unique property, a positive electrical charge. In the early, acidic oceans, many simple organic molecules like carbon dioxide and ammonia carry a slight negative charge. Opposites attract, so these molecules would have been drawn to and concentrated on the pyrite surface, held in place like iron filings on a magnet. This concentration is the first critical step, turning a dilute ocean into a ready-made reaction chamber, but pyrite is more than just a sticky trap. It is chemically active. The formation of pyrite from iron and hydrogen sulfide releases energy. Wachter's brilliant leap was to see that this very reaction, happening on the surface of a growing pyrite crystal, could provide the power to drive other chemical transformations. Imagine carbon dioxide stuck to that pyrite surface. The energy from the pyrite formation could be used to strip that inert gas apart and reassemble its carbon into the backbone of more complex organic molecules like acetic acid or even amino acids. This is the heart of an autotrophic origin, meaning life that builds itself from the ground up, from simple inorganic compounds like carbon dioxide, rather than consuming pre-made organic soup. In this view, the first living system was not a cell. It was a two-dimensional chemical film, a metabolic crust catalyzed by iron and sulfur minerals. This crust would have grown, spreading across the mineral surface as it converted more ocean chemicals into its own substance. Reproduction at this stage would have been simple, almost geological, as flakes of this active crust broke off and settled on fresh pyrite surfaces, seeding new colonies of the chemical reaction. It was a living chemistry before it was a living organism. Only much later, as this surface metabolism grew more sophisticated, would it have learned to build a container, a lipid membrane, to enclose its chemistry and float free from the mineral scaffold that gave it birth. This flips the traditional story on its head. Genetics and replication are not the starting pistol of life, but brilliant inventions that evolved later to stabilize and standardize a metabolic process that was already humming along, powered by the slow burn of iron and sulfur on the rocky floor of an ancient sea. But the energy of pyrite is just one kind of planetary fire. Beneath the surface of the early Earth, another, far more potent power source was quietly decaying, offering a different kind of spark. This is Theory 13, the world of the radioactive beach. Before life, before even stable continents, the planet was a geologically violent place, rich with heavy elements forged in the explosions of ancient stars. Among these were unstable, radioactive isotopes like uranium-235, potassium-40, and thorium. These elements were more abundant on the early Earth than they are today, their energetic half-lives slowly ticking down over billions of years. Where did they collect? Often in dense, sandy deposits along the shores of the first proto-continents, concentrated by the action of waves and currents. Picture a stark, black sand beach under an alien sky. The sand isn't just silicate, it's speckled with grains of uranium ore and other radioactive minerals. These tiny grains are constant, silent power cells. As their atoms decay, they emit a steady barrage of energy in the form of alpha and beta particles and gamma rays. This radiation is a double-edged sword. In high doses, it shatters complex molecules, but in the right setting, it becomes a potent driver of chemical change. Imagine a shallow lagoon just behind this beach, fed by freshwater streams and the tide. Water percolates down through the sand, coming into close contact with these radioactive grains. The radiation passing through the water has enough energy to rip molecules apart, creating a soup of highly reactive fragments called free radicals. These radicals are desperate to form new bonds, and in doing so, they can build molecules that are more complex than the ones they destroyed. The radioactive grains act like microscopic reactors, their decay providing a relentless, localized source of energy to drive prebiotic synthesis in the water and wet sediments surrounding them. This environment solves several problems at once. It provides a steady, long-term energy source independent of sunlight or volcanic heat. The water acts as both a solvent and a moderator, absorbing and distributing the radiation's energy, preventing it from being purely destructive. And perhaps most importantly, it creates a gradient. The radiation is most intense right at the surface of the mineral grain, fading with distance. This sets up zones of different chemical activity, a natural laboratory where different reactions could occur at different ranges from the power source. One reaction might happen in the intense zone closest to the uranium grain, producing an intermediate compound that then drifts a few micrometers away into a milder zone, where it becomes the ingredient for the next step in a chain of synthesis. It's a slow, patient chemistry powered by the deep time heartbeat of atomic decay. While not as visually dramatic as a volcanic vent, the radioactive beach presents a compelling niche. It suggests that life's precursors could have been cooking in many quiet, unassuming places, wherever water met a concentrated source of this primordial atomic energy. The very stones beneath their feet, ticking with the slow fire of a dying star, could have been the engines that first stirred the inert chemicals of the young world toward something new. Radioactive sands offered a quiet, terrestrial forge, but the most spectacular deliveries may have arrived from the heavens in a blaze of fire and ice. Theory 14 narrows the vast idea of panspermia to a single, dramatic messenger, the cometary delivery theory. To understand its promise, you must first see a comet for what it truly is, not just a streak of light in the sky, but a preserved relic of the solar system's birth. Astronomers often call them dirty snowballs, but that humble name belies their complexity. A comet is a mountain of ice, but that ice is not just water. It is a frozen archive containing a stunning array of molecules: carbon dioxide, methane, ammonia, and more critically, complex organic compounds. Spectroscopic analysis and missions like the European Space Agency's Rosetta, which visited Comet 67P, have confirmed their presence: amino acids, the sugar glycolaldehyde, and even phosphorus, a key element in our genetic backbone. These icy bodies are cosmic freezers, having drifted in the deep cold of the outer solar system for billions of years, perfectly preserving this primordial chemical cocktail. Now envision one such comet nudged by a gravitational tug, beginning a long fall toward the inner solar system and a collision course with the young Earth. The impact would have been cataclysmic, releasing energy equivalent to millions of nuclear bombs. The surface of the comet would vaporize instantly in a flash of intense heat and pressure. For decades, scientists assumed such an impact would be purely destructive, sterilizing any delicate organics within. But more recent research reveals a fascinating paradox. While the initial shockwave is devastating, the conditions inside the comet's core during atmospheric entry and impact are not uniformly destructive. The outer layers may vaporize, but the inner core can be compressed and heated in a more gradual, controlled manner. This sudden, intense pressure cooking can actually drive chemical synthesis, forging new, more complex organic molecules from the simpler ones already present. The impact itself becomes a reactor, not just a destroyer. This leads to the theory's most provocative suggestion. perhaps comets delivered more than just a random assortment of ingredients. Within the protective, deep frozen interior of a large comet, shielded from radiation for eons, probiotic chemistry had ample time to experiment. The constant, gentle background radiation from space could have driven reactions in the ice over millions of years, potentially creating not just amino acids, but linked chains of them, or membrane-forming lipids or other protobiological structures. When such a comet struck Earth, it is possible that not everything was obliterated. Chunks of the inner core, especially if they landed in a cool ocean or a muddy basin, could have deposited these partially formed, complex chemical systems intact. In this view, Earth did not have to start from absolute scratch. It received a pre-assembled toolkit, a jump-started chemistry set that had been slowly assembling in the deep freeze of space, delivered in a dramatic moment of cosmic gardening. The comet becomes the ultimate seed pod, carrying within its icy heart not just the promise of life, but perhaps its halfway constructed blueprint. The violent arrival of a comet delivered a frozen toolkit, but where on Earth was the gentlest place to open it? Charles Darwin himself once privately pondered a far more serene birthplace. In a famous letter written in 1871, he speculated about a warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity present. This simple, elegant image is Theory 15, the tidal pool. Picture a sheltered inlet on the early Earth's coastline, a shallow basin carved from volcanic rock or nestled between ridges. It is not the deep, pressurized darkness of a vent, nor the frozen stillness of an ice world. It is a sunlit laboratory, open to the sky but protected from the full fury of the open sea by a natural barrier. This tidal pool becomes a dynamic mixing bowl for the planet's richest chemistry. Freshwater streams trickle down from the land, carrying dissolved minerals and clays eroded from the rocks. The tide itself surges in daily, bringing a fresh supply of ocean water, rich with the organic compounds formed in the atmosphere or delivered by meteorites. With each tidal cycle, the pool's contents are stirred, creating new combinations of ingredients. The sun provides a steady, gentle warmth, encouraging chemical reactions without the destructive intensity of the wider ocean surface. But the true genius of this environment lies in its rhythm of concentration. During low tide, under the sun's heat, the water in the shallow pool begins to evaporate. As it does, everything dissolved within it becomes more concentrated. Amino acids, lipids, and salts that were once diluted are now pushed together, dramatically increasing their chances of interacting and linking up. The edges of the pool, where water meets rock and clay, become particularly active zones. The clays, with their charged surfaces, act as catalysts and templates, holding organic molecules in place and encouraging them to form longer chains. Then the high tide returns, flushing the pool with cool, fresh water and new chemicals. This new influx can trigger a different set of reactions or protect the newly formed polymers from breaking down under the prolonged heat. This daily cycle of wetting and drying, of dilution and concentration, acts like a natural, rhythmic pump. Each tide is a chance to shuffle the deck, to test new combinations, and to preserve the most stable results. Darwin's warm little pond, updated with our modern understanding, is a bioreactor powered by planetary rhythms. It combines the best of many worlds, the catalytic power of minerals from the clay hypothesis, the concentration effects of the ice world, and the gentle thermal energy of the sun. It is a place where the building blocks from comets and atmospheric chemistry could meet, mingle, and be patiently assembled into something greater by the patient, ceaseless pulse of the moon's pull and the sun's warmth. It feels intuitively right, a cradle that is both nurturing and creative, offering not just ingredients and energy, but the perfect, repeating conditions to turn randomness into order. The surface world was a dangerous place, but beneath the violence lay a sanctuary of profound stability. Theory 16 proposes an underground origin where life did not brave the storm but retreated from it entirely. The early Earth's surface was a relentless battleground. A faint young sun provided little protection, allowing intense ultraviolet radiation to scorch the land and sea. This was compounded by the late heavy bombardment, a period when asteroids and comets rained down in a celestial onslaught that would have sterilized any fragile chemistry taking hold in shallow pools or on beaches. For life's first delicate experiments, the surface was the worst possible laboratory. The solution was to go down deep into the planet's crust. Just a few meters beneath the surface, the rock itself becomes a perfect shield. It blocks the deadly UV radiation entirely. It buffers against the temperature extremes of day and night, and even during a massive asteroid impact while the surface is vaporized, the shockwave attenuates rapidly with depth. The subterranean world offered a quiet, dark, and remarkably consistent environment, insulated from the apocalyptic chaos above, but this was not a barren tomb. The deep crust was, and still is, geologically alive. Water seeps down through fractures and pores, coming into contact with hot, iron-rich rocks like olivine, a major component of Earth's mantle. This triggers a chemical reaction called serpentinization. As the water reacts with the rock, it transforms the minerals, but more importantly, it releases hydrogen gas. Hydrogen is a powerful reducing agent, a chemical that eagerly donates electrons. In the presence of carbon dioxide, which also permeates the subsurface, this hydrogen can drive reactions that form simple organic molecules like methane and formate. Here, in the absolute darkness, with no energy from the sun, a completely different kind of metabolism could have sparked. The heat from the Earth's interior provides gentle, persistent warmth, while the serpentinization reaction provides a steady, reliable food source, hydrogen. This is the exact energy strategy used by some of the most ancient lineages of microbes we find today, deep underground organisms that live off hydrogen and carbon dioxide, a process called chemosynthesis. The theory suggests these modern deep dwellers are not strange outliers, but living fossils, still inhabiting the very type of environment where life first learned to harness chemical energy. The porous, water-filled fractures in the rock would have served as a vast, interconnected network of microscopic chambers, each a potential incubator. Within these rocky pores, the first metabolic networks could have established themselves, fueled by the planet's own geochemistry, safe from the extinction-level events happening overhead. It paints a humbling picture that we and every living thing on the surface may be the descendants of refugees, of pioneers who first found life not in the light, but in the enduring, nurturing dark of the world's stone heart. The deep crust offered safety, but the surface held a power far more abundant and relentless. Theory 17, the photochemical origin, argues that the very thing which made the early Earth's surface so dangerous, ultraviolet light, was also its greatest creative force. Without a protective ozone layer, the young planet was bathed in intense, unfiltered UV radiation from the sun. We think of this as purely destructive, capable of breaking apart the delicate molecules of life. Yet, in the right chemical context, that same furious energy can be a master builder. Photochemistry is the science of using light to drive chemical reactions. On the early Earth, the atmosphere was a vast, open-air reactor. Simple gases like hydrogen cyanide, methane, and water vapor swirling high above the planet were continuously zapped by this solar energy. The photons of UV light carry enough punch to break the chemical bonds in these simple molecules, creating a soup of highly reactive fragments. These fragments don't just float apart. They immediately crash into each other, recombining in new, often more complex arrangements. Laboratory experiments have brilliantly demonstrated this process. When scientists simulate the early atmosphere and shine strong UV light onto a mixture of simple precursors like hydrogen cyanide and water, something remarkable happens. They don't just get broken scraps, they witness the formation of nucleobases, the very information-carrying letters of RNA and DNA, such as adenine and guanine. They can also produce sugars and amino acids. This isn't a gentle simmering, it is a forge where the hammer of sunlight pounds simple atoms into the sophisticated shapes life requires. This process wouldn't have been confined to the sky. The same intense UV light would have played upon the surface of the early oceans and lakes. Here, any organic compounds that formed in the atmosphere and rained down or that were present from other sources would have been further processed. The light could drive reactions on the surface of clays or in evaporating tidal pools, linking small molecules into chains or rearranging them into more stable, biologically relevant forms. In this view, the first complex organic molecules were not hidden away in the deep. They were literally painted across the sky and seen by the sun itself, a daily, global phenomenon. Life's ingredients were not rare treasures, but a constant, raining drizzle of solar-made complexity. The photochemical origin theory presents a powerful duality. The same UV radiation that created a deadly barrier for early life also manufactured the very pieces needed to eventually overcome it. It suggests that life's story began not in spite of the harsh conditions, but because of them, forged in the brilliant, unforgiving light of a star that had not yet been told to stand back. But perhaps we have been asking the wrong question. We search for the one true cradle, the single spark that ignited everything. Theory 18, the multiple origins theory, proposes a radical shift in perspective. What if life did not begin once but many times? The early Earth was not a single, uniform laboratory. It was a planet of incredible diversity, offering dozens of plausible crucibles. Deep sea vents hummed with chemical energy, sunlit tidal pools concentrated and cycled their ingredients, icy worlds provided protective stillness, radioactive beaches pulsed with atomic decay. In each of these distinct environments, the same fundamental processes of chemistry and physics were at play. Given enough time and the right ingredients, the leap from non-living to living might not be a miraculous fluke but a probable outcome. This theory suggests that in many of these places, perhaps even in all of them, primitive, self-sustaining chemical systems flickered into existence. They would not have been life as we know it, but varied experiments in proto-living, each shaped by its unique environment. A metabolic crust on a vent mineral might have been very different from a replicating molecule in an icy pocket or a growing vesicle in a warm pond. For a time, the young planet could have been a mosaic of these different biological startups, each with its own strengths and weaknesses. Then comes the most fascinating possibility: competition and collaboration. These early experiments were not isolated. Through tidal flows, groundwater movement, or even atmospheric circulation, their components could have mixed. Imagine a lipid vesicle formed in a hot spring washing into the ocean, where it encounters a strand of replicating RNA that had been sheltered in sea ice. Could they have merged, combining the vesicle's protective container with the RNA's information-carrying ability? Or perhaps a successful metabolic cycle from a deep crust fracture was swept upward, finding a mineral catalyst on a beach that made it far more efficient. In this bustling probiotic world, the most robust systems wouldn't just outcompete the others. They might literally incorporate the best ideas from their rivals. What we call life today, with its universal genetic code and core biochemistry, may not be the descendant of a single winner, but the ultimate hybrid, a chimera built from the most successful innovations of countless failed experiments. It is the one lineage that learned to borrow, adapt, and integrate, becoming so versatile that it could eventually colonize every niche and eclipse all other origins. This view transforms the search from a quest for a singular birthplace to an appreciation of a planet-wide process of trial and error, where life, in many forms, was testing itself against the world long before the first true cell ever swam. Metals were the silent partners in this ancient chemistry, and one in particular may have held the key to harnessing light itself. Theory 19, the zinc world hypothesis, focuses on a humble but brilliant mineral, zinc sulfide. This crystalline compound, often found shimmering around deep-sea hydrothermal vents in a form called sphalerite, is more than just a geological curiosity. It is a natural semiconductor, a material with the same basic properties as the solar cells we use today. On the early Earth, before the ozone layer existed, the ocean's surface was awash with the sun's punishing ultraviolet light. But at certain depths around vents where zinc sulfide crystals grew, this destructive energy could be transformed. When a UV photon strikes a zinc sulfide crystal, it excites electrons, kicking them into a higher energy state. These excited, energetic electrons are desperate to find a new home, and that desire can be harnessed to do chemical work. The theory proposes that these mineral surfaces, buzzing with photo-excited electrons, became the world's first solar panels. Imagine carbon dioxide dissolved in the seawater drifting over a bed of these glittering crystals. The energized electrons on the crystal's surface could have been donated directly to the carbon dioxide, driving a chemical reduction. This process would strip away oxygen atoms and begin building the carbon into more complex, energy-rich organic molecules like formic acid or formaldehyde. It is a primitive form of photosynthesis, but one performed entirely by rocks, using sunlight to fuel the fundamental conversion of inorganic carbon into organic building blocks. This zinc world provides an elegant bridge between the chemical energy of the deep vents and the abundant solar energy of the surface. It suggests life's first metabolic trick might not have been to eat chemicals from a vent, but to eat sunlight with a mineral acting as the intermediary. Life, in this view, began as a photochemical film, a partnership between incoming starlight and a crystalline semiconductor that knew how to listen. The first stirrings of biology were not in the dark, but in the dappled, shimmering light filtering down to where geology learned to breathe with the sun's own rhythm. The sunlit chemistry of zinc sulfide required a stable home, a place where fleeting reactions could become lasting cycles. Deep within certain volcanic rocks, a perfect architecture for this purpose already existed, carved not by life but by geology itself. Theory 20 explores the world of gas-filled pores in rocks. Submarine lava flows, when they cool rapidly underwater, do not form solid, impenetrable barriers. Instead, they become like a mineral sponge, riddled with a labyrinth of microscopic bubbles and interconnected channels. These are vesicles, tiny cavities frozen in time from the moment the lava solidified around pockets of escaping gas. This porous rock becomes something extraordinary, a natural, three-dimensional laboratory with billions of tiny, isolated chambers. Each microscopic pore is a potential incubator, a sealed room only a few millionths of a meter across. Within these rocky compartments, the conditions for life's emergence are met in a beautifully simple way. First, they solve the problem of concentration. In the vast, open ocean, interesting molecules might drift apart forever, never meeting to react. But in a porous rock, water percolating through the network carries these molecules into the pores where they become trapped. Evaporation or further chemical processes can then concentrate them, dramatically increasing the odds of a productive collision. Second, the walls of these pores are not inert. They are made of volcanic minerals like olivine or pyrite, surfaces rich in iron, nickel, and sulfur. These metals are powerful catalysts, the very same ones that life's enzymes use today to speed up critical reactions. A molecule stuck to the pore wall isn't just waiting, it's being actively encouraged to transform, to link with its neighbor, to build complexity. Most importantly, these pores provide compartmentalization without requiring a biological membrane. Each tiny cavity is a naturally formed cell wall made of stone. It separates its internal chemical experiment from the outside flow, allowing different pores to develop different chemical specialties. One pore might by chance become adept at producing a certain type of amino acid. The pore next door might excel at stringing them together. Because the pores are connected by tiny channels, the products of one can diffuse to the next, creating a primitive, rock-based assembly line. In this view, the first metabolic networks weren't free-floating. They were literally etched in stone, a slow, silent chemistry humming in the dark cavities of submarine rock. These gas-filled pores offered protection, catalysis, and organization, all from a simple geological process. Life, then, may have begun not as an invasion of the planet, but as an awakening within its very bones, a whisper of chemistry that learned to echo in the endless tiny rooms of a volcanic vault. While the rocky pores of the seafloor offered a stable home, the cradle of life might have been far less anchored. It may have floated high above the planet, dancing on the winds. Theory 21 lifts our gaze to the aerosol droplet theory, where the sky itself becomes a billion tiny laboratories. In the early atmosphere, vast clouds of organic haze would have shrouded the young Earth, not unlike the smoggy orange skies of Saturn's moon Titan. This haze was made of countless microscopic droplets, aerosols, each one a self-contained world. Formed from gases like methane and nitrogen reacting under ultraviolet light, these droplets were more than just specks of mist. They were hyper-concentrated chemical reactors, trapping and concentrating the very organic molecules that were forming in the atmospheric soup. Inside each minuscule droplet, the rules of chemistry changed. Molecules that would rarely meet in the vast openness of the air were now forced into intimate contact, packed into a tiny, liquid volume. Here, they were bathed in a constant bath of energy, from the relentless UV sunlight to the crackling charge of atmospheric electricity from lightning storms and auroras. This energetic environment could drive reactions at a furious pace, linking simple carbon chains into more complex structures, perhaps even forming the precursors to amino acids or nucleotides. The life cycle of these droplets added another critical layer. They didn't just hover forever. Through collisions, tiny droplets would coalesce into larger ones. As they grew heavier, they would eventually succumb to gravity, falling from the sky as a gentle, organic rain. This wasn't water alone. It was a drizzle of concentrated, chemically enriched material, a continuous delivery service from the atmospheric factory to the waiting oceans below. Each raindrop was a payload, seeding the surface waters with a fresh supply of pre-processed complex compounds. This process turns the entire planet into a linked system. The atmosphere acts as the primary forge, using solar and electrical energy to build complexity. The falling rain acts as the distribution network, constantly feeding this output into the various surface incubators, the tidal pools, the clays, the icy layers. The aerosol droplets provide an elegant solution to the concentration problem on a global scale, and they do it with a dynamic, cyclical rhythm. The sky wasn't a passive ceiling, it was an active participant, brewing the ingredients for life in its luminous, stormy heights and showering them down upon the world day after day for millions of years. The molecules of life possess a secret-handedness, a preference so absolute it defies random chance. In every known living organism, from the smallest bacterium to the largest whale, the amino acids that build proteins are exclusively left-handed. The sugars that form the backbone of DNA and RNA are exclusively right-handed. This universal bias is called homochirality, and it presents a profound puzzle known as the chiral selection problem. Why would life, emerging from a soup of chemicals that should have produced equal amounts of left and right-handed versions, choose only one? It is a mystery any complete origin story must eventually solve, because without this uniformity, the complex machinery of life simply cannot function. Imagine trying to build a machine where half the screws were threaded clockwise and the other half counterclockwise. The pieces would not fit together. In the same way, a right-handed amino acid cannot properly link into a protein chain designed for left-handed ones. The precision of biology demands a single, consistent choice. So how did a random, non-living world make that first decisive selection? One compelling idea looks to the stars, specifically to the violent death throes of massive suns. When certain neutron stars spin, they can emit intense beams of circularly polarized light. This is light whose electric field rotates in a specific direction, either clockwise or counterclockwise, like a corkscrew. As this twisted starlight traveled across the galaxy, it could have irradiated the vast molecular clouds where prebiotic compounds were forming on dust grains. Experiments show that circularly polarized light can selectively break down one chiral form of a molecule over the other. Over eons, this subtle but persistent cosmic bias could have imprinted a slight excess of one-handedness into the organic material that eventually seeded our solar system. A more terrestrial source might lie in the weak nuclear force, one of the four fundamental forces of the universe. This force has an inherent handedness of its own, and it influences the decay of certain radioactive isotopes like potassium-40, which was abundant on the early Earth. As these atoms decay, they emit spin-polarized electrons, particles with a specific orientation. These electrons, when they interact with prebiotic molecules, could have preferentially destroyed or transformed one chiral form, leaving behind a slight surplus of the other. The final step from a slight surplus to absolute dominance might have occurred through a simple, elegant process on a rocky shore. In a tidal pool undergoing wet-dry cycles, a tiny crystal of a pure chiral form could have acted as a seed. As the solution evaporated, molecules of the matching handedness would preferentially latch onto the growing crystal, amplifying that form's presence in the remaining liquid. With each cycle, the imbalance grows until one form is completely consumed, leaving a pool of perfectly uniform, left-handed amino acids ready for the next step toward life. Homochirality is not just a quirky detail, it is a fundamental signature, a fingerprint that may tell us whether life's choice was guided by the spin of a dying star, the quiet decay of a rock, or the patient rhythm of the tides. The absolute handedness of life's molecules suggests a world already leaning toward order. But what if that order was forged in conflict, in a microscopic war that predates life as we know it? The virus-first hypothesis turns our entire understanding of the biological hierarchy upside down. We are taught that viruses are degenerate hitchhickers, stripped-down fragments of genetic code that can only replicate by hijacking the sophisticated machinery of a living cell. They are the ultimate parasites dependent on a host that must have evolved first. But this theory asks a daring question. What if that dependency is not a sign of lateness but of primacy? Imagine the prebiotic world not as a quiet laboratory, but as a chaotic molecular frontier. In this realm, the first self-replicating molecules, perhaps simple strands of RNA, have already emerged. They copy themselves, compete for resources, and evolve. But replication is imperfect. Some strands make mistakes, forming variants that are not just copies, but can interact with other molecules in new ways. Among these variants, a revolutionary innovation occurs, a molecule that learns to wrap itself in a protective coat, a simple shell made from available proteins or lipids. This is not a cell, it is something far simpler, a naked gene with a cloak, a protovirus. This coat does more than protect. It allows the genetic core to survive harsh conditions, to drift to new locations, and most critically, to recognize and latch onto other replicating molecules. In this view, the first viruses were not parasites of cells, but parasites of each other and of any free-floating genetic material. They were molecular predators and scavengers in a soupy wilderness. This sets the stage for an ancient arms race, a relentless evolutionary pressure that would shape the future of all life. If you are a replicator without a coat, you are vulnerable to being co-opted or destroyed by those who have one. The selective advantage for building defenses becomes immense. One powerful defense would be to enclose your own genetic material and metabolism within a durable, fortified barrier, a lipid membrane. Another would be to develop internal machinery for replication, so you are not reliant on the chaotic chemistry of the open environment. In essence, a cell could have evolved as a castle, a secure citadel built to protect a precious genetic lineage from the viral raiders swarming outside. The cellular world, with all its complexity, might be the consequence of an endless siege. The evidence for this is written into our own biology. A staggering portion of the genomes of all complex life, including humans, is made of viral DNA, remnants of ancient infections that became permanent residents. These are not just scars, they have been co-opted for essential functions, like the formation of the placenta in mammals. This suggests a deep, ancient relationship, a fusion of worlds that began not as an invasion of established life, but as a partnership or a truce between competing replicators from the dawn of time. The virus first idea reframes our origins in a dramatic light. It paints the earliest biosphere as a turbulent genetic free-for-all, where the drive to survive and copy oneself created both the predator and the prey, and where the ultimate defense was to build a living home and lock the door behind you. The fundamental laws of our universe feel like fixed, unchangeable rules, but physics reveals they are built upon a series of delicate numerical balances. The strength of gravity, the force binding the nucleus of an atom, the precise mass of an electron. If any of these constants were altered by even a fraction of a percent, the cosmos as we know it would not exist. Stars would not ignite, carbon would never form in stellar furnaces, and complex chemistry would be impossible. This remarkable precision is known as cosmic fine-tuning, and it presents a breathtaking backdrop to our origin story. It suggests the stage itself was set with meticulous care for the eventual appearance of life. One profound interpretation of this fine-tuning is the anthropic principle, a perspective that intertwines physics with a deep philosophical observation. In its simplest form, it states that the universe must be compatible with the conscious life that observes it, because we are here to observe it. This might sound circular, but its power emerges when we consider scale. If our universe is just one bubble in a vast, perhaps infinite multiverse, where each bubble has a random set of physical laws and constants, then most of those universes would be stillborn or barren. They would flash into existence with laws too weak for structure or too violent for stability. In that unimaginable sea of failed cosmoses, a tiny fraction, by pure statistical chance, would have the perfect golden combination that allows for galaxies, planets, and biochemistry. We inevitably find ourselves in one of those rare, habitable bubbles, not because it was designed for us, but because we could not arise anywhere else. From this vantage point, the origin of life is not a lucky accident on a single planet, but an inevitable flowering in a universe whose very bedrock is fertile. The long chemical journey from interstellar clouds to self-replicating cells was not a struggle against the universe's nature, but a direct consequence of it. The fine-tuning does not answer how life began, but it profoundly reshapes the why. It frames our entire existence as a natural product of a cosmos that is, at its heart, bio-friendly. This perspective is both humbling and empowering, suggesting that in the grand lottery of cosmic possibilities, we hold the winning ticket, not through divine favor, but through the relentless statistical patience of reality itself. Quantum mechanics is not just the physics of the tiny, it is the operating system of reality itself. At the scale of atoms and electrons, the rules of our everyday world dissolve into a realm of probabilities where particles can be in two places at once, tunnel through impossible barriers, and remain mysteriously connected across distance. These are not abstract curiosities confined to supercooled laboratories. A revolutionary idea, Theory 25, the quantum biology origin, proposes that these very phenomena were active, essential participants in the drama that birthed life. It suggests the first living system did not just emerge from chemistry, but from chemistry dancing to the quantum tune. Consider the very first energy transfers, the moment a spark of useful power had to jump from a mineral surface to a waiting molecule or between two delicate protoenzymes. In our classical world, this requires a precise high-energy collision. But in the quantum world, particles like electrons do not always need to go over an energy barrier. They can cheat through a process called quantum tunneling. An electron can simply disappear from one side of a chemical barrier and reappear on the other, as if the obstacle wasn't even there. This isn't magic, it's a fundamental property of matter at the smallest scales. If such tunneling was at play in the structured environments of hydrothermal vent pores or on catalytic clay surfaces, it could have made the earliest, most fragile energy harvesting reactions startlingly efficient. A reaction that would be too slow or improbable under classical rules could become viable, even likely, giving a crucial advantage to the first metabolic loops. The quantum advantage might extend to life's most puzzling signature, its uniform-handedness. How did a racemic mix of left and right-handed molecules commit entirely to one side? Quantum mechanics offers a fascinating, if speculative, pathway. Some experiments suggest that the subtle interplay between the spin of an electron and the chirality of a molecule can create a tiny energy difference between the two mirror image forms. This difference, magnified over millions of amplification cycles in an evaporating tidal pool, could have tipped the scales decisively. The universe's inherent quantum bias, written into the fabric of matter, might have been the invisible hand that made the first fateful selection. The most profound quantum proposal involves coherence and entanglement. In our warm, wet world, we think quantum states are fragile, destroyed by the slightest disturbance. But what if the first life was not warm and wet in a chaotic way? What if it existed in a highly ordered, crystalline-like environment, such as within the layered structure of certain minerals or the organized water molecules at a mineral interface? In such a protected niche, quantum coherence, where particles act in a unified wave-like state, could have been maintained long enough to matter. Imagine a network of pigment-like molecules conducting the energy from a proton gradient or sunlight not as a random hop, but as a coordinated quantum walk, finding the most efficient path with almost no loss. This isn't just efficient, it's smart, a form of quantum computation solving the problem of energy distribution before a brain or even a cell existed. This theory does not replace the chemical narratives of vents or tidal pools. Instead, it infuses them with a new layer of potency. It proposes that the cradle of life was not just a chemical reactor, but a quantum chemical reactor. The transition from non-life to life may have been the moment when a system of molecules became organized enough to capture and utilize the strange, probabilistic magic of the quantum realm, harnessing superposition and entanglement to perform the first tricks of biology. It is a breathtaking synthesis suggesting that life, in its deepest essence, might be a macroscopic expression of quantum ingenuity, a testament to the fact that the universe's most exotic physics was there at the very beginning, waiting in the quiet to be awakened. This planetary perspective invites us to think on the grandest scale of all. Theory 26, the living Earth, asks us to see our planet not as a rock that life colonized, but as a single, integrated system where biology and geology are two expressions of the same continuous process. It is the Gaia hypothesis extended back to time's very beginning. The idea, in its essence, is that life is not a passenger on Earth. It is a behavior that Earth learned to perform. From this viewpoint, the search for the first organism is a kind of mirage, because the transition from non-living to living was not a sudden spark, but a slow, planetary-scale awakening. Imagine the young Earth as a dynamic, churning chemical engine. Volcanic outgassing built an atmosphere, water condensed into oceans, minerals weathered and reacted. These geochemical cycles were already a form of planetary metabolism, moving energy and matter in vast, repeating loops. Now, introduce the first self-sustaining organic reactions, perhaps on a vent mineral or in a tidal pool. These new chemical networks did not appear in isolation. They were plugged directly into the planet's existing flows. They began to subtly alter the chemistry of the water around them, consuming some compounds and releasing others. As these proto-living systems spread and diversified, their collective chemical activity became a new, powerful force in shaping the environment itself. The line between the living and the non-living blurs into irrelevance. Was it the iron-sulfur crust that was alive, or the entire vent field it was part of? Was it the replicating RNA strand, or the evaporating tidal basin that concentrated and protected it? The theory suggests there is no correct answer because life emerged as a property of the whole interconnected system. There was no single moment of creation, only a gradual increase in the complexity, efficiency, and self-regulation of Earth's surface processes. The planet began to manage its chemistry with greater finesse, using these new organic catalysts to accelerate certain reactions, to stabilize temperature ranges, to build feedback loops. In this grand narrative, the first true cells were not the beginning of life, but a later milestone. A moment when the planetary biosphere invented a highly successful, portable unit for carrying out its ongoing work. They were like specialized organs emerging within a larger planetary body. This view dissolves the mystery of the first spark into a deeper, more continuous mystery, the emergence of a self-regulating, creative complexity from the raw flows of planetary energy. It implies that if we ever find another world with a similar dynamism between its geology, atmosphere, and chemistry, we might not find a lone microbe. We might find a planet already humming with a coherence that is, for all intents and purposes, alive in its own way, waiting only for an observer to give it a name. The final frontier of this mystery may not be in chemistry at all, but in the nature of meaning itself. Theory 27, the information theory approach, reframes the entire question. What if life is not defined by what it is made of, but by what it does with knowledge? In this view, the transition from non-life to life occurred when a random collection of molecules crossed a critical threshold of organization, becoming a system that could reliably store, copy, and act upon information about its own existence. The shift is profound, moving our search from specific ingredients like RNA or lipids to an abstract, almost mathematical principle. It asks, what is the simplest physical system that can be said to have a memory, to learn from its environment, and to pass those lessons on? Imagine a simple chemical cycle, perhaps clinging to a vent mineral. It consumes hydrogen and carbon dioxide to produce methane. For a long time, it is just a reaction, a passive flow dictated by geology and thermodynamics. But then, by chance, a byproduct of this reaction forms, a molecule that happens to make the cycle run slightly faster or more efficiently when it is present. This molecule is not food, it is not energy, it is a catalyst. Now the system has a new feature. The presence of this catalyst becomes a piece of information, a bit of data that says this configuration works well. If this catalyst molecule can somehow be replicated by the very cycle it improves, then that successful configuration can be preserved. Information about a working state has been stored and copied. This is the seed of heredity. The fidelity of that copying is everything. A system that copies its successful state with perfect accuracy gets stuck, it cannot adapt. A system that copies with too many errors falls apart, losing any advantage it gained. Life, from this perspective, emerges in the narrow golden zone between stability and chaos, where information is replicated with just enough fidelity to be useful, but just enough variation to allow for improvement. It is not about the molecule, it is about the message the molecule carries. A strand of RNA that replicates itself is not alive because it is RNA. It is alive because it is a string of symbols that can be read, copied, and through mistakes rewritten. The clay crystal that replicates its defect pattern is, in a primitive sense, engaging in the same process. The lipid vesicle that inherits a slightly more stable membrane from its parent is passing on information about successful structure. This theory elegantly unites many of the disparate ideas we have explored. The deep sea vent, the tidal pool, the icy matrix, they are all potential stages where this informational dance could have begun. The specific chemistry is almost secondary, a local dialect. The universal language is the feedback loop between a system, its environment, and its ability to record what works. It leads us to a breathtakingly broad definition of life, any self-sustaining system capable of Darwinian evolution. This means we might one day recognize life in a swirling pattern of energized dust in a plasma cloud, or in a pulsating network of chemical reactions in a subterranean aquifer, systems that look nothing like cells but that nonetheless remember, adapt, and learn. The origin of life, then, becomes the origin of meaning in a universe of blind force, the moment when physics first began to keep a diary. The evidence for life's antiquity is etched into the oldest rocks we can find. In formations in Greenland and Australia dating back over 3.8 billion years, scientists see tantalizing chemical signatures, isotopic hints that something biological was already at work, pulling carbon from the air and leaving its fingerprint in the stone. This presents a staggering timeline, for the Earth itself is only about 4.5 billion years old. It suggests life got started with almost unbelievable speed, as if the moment the oceans cooled, chemistry wasted no time in crossing the threshold. But this rapid dawn clashes violently with another chapter of our planetary history, a period of absolute hell known as the Late Heavy Bombardment. For hundreds of millions of years after the planets had formed, the inner solar system became a shooting gallery. Asteroid and comet impacts of unimaginable scale were commonplace, events so powerful they could have boiled the oceans and sterilized the entire planet's surface, not once but repeatedly. How could anything as delicate as a first living cell survive that? Theory 28, the false start catastrophe, proposes a radical reconciliation. It suggests that life did indeed emerge with that breathtaking speed, not once but twice. The first genesis was a fragile, initial experiment, a tentative chemistry that had just learned to replicate in some sheltered niche. It spread, perhaps globally, establishing a foothold in those ancient seas, and then the sky fell. A massive impactor, or a relentless series of them, turned the planet into a furnace. The oceans vaporized into scalding steam, the very rocks melted. That first delicate biosphere, every last cell and chemical network, was utterly obliterated, scrubbed clean from the face of the Earth. All evidence of it, save for the most ambiguous chemical whispers, was erased. After the bombardment finally subsided, the planet cooled again. The oceans recondensed from the steamy atmosphere. And in this new, quieter world, the process began again. But this second genesis was not starting from scratch. The planet was now seeded with the organic wreckage of the first life, the broken fragments of its molecules scattered everywhere. It was like a forest fire that burns everything to ash, but in that ash are the nutrients for a new, hardier forest to grow. The second origin had a richer, more complex chemical palette to work with, and it unfolded in an environment that was finally stable enough to allow for long-term evolution. The life we see today, from bacteria to blue whales, would then be the descendant of this second, more fortunate beginning. This theory elegantly solves the chronological puzzle. It allows for those incredibly ancient chemical signatures to be real, the last ghostly echoes of a world that was completely lost. It also explains why we cannot find a smooth, continuous fossil record stretching back to the very beginning, because there was a reset button, a planetary-scale sterilization event that created a clean break between two separate biological histories. It forces us to consider a humbling possibility that we are not the first attempt this planet made at life. We are the survivors, the second draft written after the first manuscript was thrown into the fire. Our entire existence is built upon the ashes of a forgotten, older world, a testament to the universe's stubborn persistence in the face of its own violence. If life can be erased, it can also be built. The most direct path to understanding creation is to attempt it yourself. This is Theory 29, the synthetic life insight, where modern laboratories become time machines, running the origin story in reverse. Scientists are not waiting to stumble upon the answer in ancient rocks. They are actively trying to construct a living system from non-living parts. This ambitious endeavor, often called synthetic biology or bottom-up biogenesis, asks a brutally simple question: what is the smallest possible set of instructions and machinery required to call something alive? The answers are refining our entire search. One pioneering approach focuses on stripping life down to its bare genetic essentials. Researchers have taken the simplest known free-living bacteria, Mycoplasma genitalium, with its relatively tiny genome of about 500 genes, and systematically deactivated genes one by one. Their goal was to find the minimal genome, the absolute core set of genetic instructions needed for independent life in a lab environment. The current estimate is astonishingly small, around 400 genes. This minimal cell is not a theoretical ghost, it has been created. It can grow and divide, but it is a fragile, dependent thing requiring a rich, pre-made broth to survive. It shows us that the first life was almost certainly not a minimal cell in our modern sense. It was likely something even simpler, a system that could build its own components from a much simpler environment. This tells origin theorists that the earliest genetic code was probably far more compact and general purpose, and that the environment itself provided many of the services that modern genes now perform. The other major branch of this work builds from the ground up, creating protocells. These are not alive, but they mimic critical behaviors of life. Scientists construct vesicles from simple lipids that can grow by absorbing new molecules from their surroundings and then divide when physically stressed, like being pushed through a tiny pore. They engineer strands of RNA that can replicate themselves inside these vesicles. They design chemical networks that can sustain a metabolic cycle within a droplet. Each successful experiment is a revelation. It reveals which steps are surprisingly easy, like membrane formation, and which are profound hurdles, like achieving accurate replication without a host of modern enzymes. These lab-born systems act as proofs of concept, demonstrating that individual pieces of the life puzzle can indeed be assembled through plausible chemistry. But the grand synthesis, getting a container, a metabolism, and a replicator to all work together sustainably, remains the monumental challenge. This struggle is itself a crucial clue. It tells us that the transition from non-life to life was likely not a single event, but a series of stages, each stabilizing the system enough for the next innovation to take hold. The synthetic approach forces a rigorous definition of life, moving beyond philosophy to engineering specifications. To be considered successfully synthesized, a system must maintain itself, grow, reproduce, and evolve. By trying to build it, scientists are mapping the exact coastline of that mysterious continent, showing us where the deep waters of chemistry end and the living shore begins. Every failed prototype in a lab narrows the possibilities for what happened on our planet billions of years ago, turning the infinite mystery into a finite and perhaps solvable puzzle. Our search has been guided by a single, powerful assumption that life everywhere must look something like us. But this final theory asks us to consider that our entire quest might be looking in the wrong place for the wrong thing. Theory 30 is the shadow biosphere, a humbling possibility that the universe's first living organism might not be a fossil, but a neighbor. We have built every one of our 29 previous theories on the foundation of life as we know it, carbon-based, water-solvent, using DNA or RNA for genetics. Our probes, our microscopes, our chemical tests, they are all exquisitely tuned to find versions of ourselves. What if we are not alone on Earth, but simply blind to our cohabitants? Imagine a microbe not from another planet but from a completely separate, forgotten genesis right here. Its biochemistry would be alien. Instead of using phosphorus in its backbone, it might use arsenic. Instead of water, its internal solvent could be liquid methane or ammonia, thriving in the supercooled lakes of Antarctica or deep underground. Its metabolism might not involve oxygen or even sulfur, but some other element we rarely consider in a biological context. To our standard tests, this shadow life would be invisible. It would not grow on our agar plates designed for carbon-based life. Its DNA would not amplify with our primers. It might not even be made of cells as we recognize them, but exist as a mineral-encrusted film or a free-floating chemical network. We would walk past it, drill through it, and never know it was there because our tools are built to see only one color in the spectrum of life. The implications are staggering. It means the first organism or its direct descendants could still be living among us, a living fossil from an alternative origin story that has persisted in some extreme niche for billions of years. It means abiogenesis might not have been a single, rare event, but something that happened multiple times, with our lineage simply being the most aggressive and successful, the one that conquered the planet and drowned out the others. Finding such a shadow biosphere would be the most profound scientific discovery in history. It would prove that life is not a fluke, but a common, even inevitable, expression of cosmic chemistry. It would mean the universe is likely teeming with life, but that much of it could be so fundamentally different that we might not recognize it even if it were in front of us. This theory is not a dismissal of all our previous searching. It is the ultimate expansion of it. It asks us to redefine our very definition of life, to build new tools that look for function rather than familiar form, to seek out complexity and energy use in places we have declared barren. It transforms Earth from a planet with one known history of life into a potential archive of multiple biological experiments. The final answer to the mystery of the first organism may not lie in a distant past or on a faraway world. It could be here now, in the cracks of a desert rock or the depths of an acidic mine, waiting for a generation of scientists bold enough to question their most basic assumptions and finally learn how to see. We have journeyed across 30 landscapes of possibility, from the simmering depths of volcanic vents to the frozen, silent chemistry of interstellar space. Each theory is a testament to human curiosity, a different path through the same profound darkness, searching for that first flicker of light. The sheer diversity of these ideas reveals a beautiful truth. There is no single, simple answer waiting for us in the rocks. The origin of life is not a puzzle with one missing piece, but a mosaic whose full picture we are still assembling from fragments of chemistry, geology, physics, and biology. This quest forces these sciences to speak to each other, weaving a story where the spin of a neutron star might influence the handedness of a molecule in a tidal pool, where the geology of a young planet sets the stage for its own biological awakening. It demonstrates that our existence is not an isolated event, but a thread woven from the fundamental fabric of the cosmos, dependent on the fine-tuning of universal constants, the violent lives and deaths of stars, and the patient, churning processes of a cooling world. These theories, in all their variety, tell us something essential about our place in the universe. They suggest that life is not a miracle in the sense of a violation of nature's laws, but a miracle of emergence, a stunningly complex pattern that naturally arises when matter and energy are given enough time and the right conditions to dance. Whether we are the product of a deep earth crucible, a celestial delivery, or a planetary-scale metamorphosis, the story of our beginning is the story of the universe becoming conscious of itself. Now we turn this question over to you. After this journey through cosmic kitchens and primordial experiments, which idea lingers in your mind? Does the elegant simplicity of the RNA world feel like a key, or does the grand, interconnected vision of a living Earth resonate more deeply? Perhaps the shadow of a forgotten biosphere fires your imagination. the conversation does not end here. Share your thoughts in the comments below. Let us know which theory feels like it holds a piece of the truth. If you crave more journeys to the edge of understanding, be sure to subscribe for deeper dives into the universe's greatest mysteries. Keep wondering, keep questioning, and never stop marveling at the greatest story ever told, the story of how everything began and how we came to be here to tell it.